Okay, the slides will be available on that website in few seconds. So I was still making some changes late last night, and then I thought that okay, in the morning I will put them up there, and forgot. For background, why I'm so interested in specifically predictive performance. This is one of my first projects, predicting concrete quality. This is wet concrete, and one of the quality properties we wanted to predict was workability. And the way they measure workability is that they take a bucket of wet concrete, pour it on the board, and then they measure how much it slumps. You can see behind that wet concrete there's a measurement stick, and they just measure how many centimeters it slumps. If it's too wet, it slumps too much, and if it's too dry, too stiff, it doesn't slump enough. And then it would be really hard to work with really stiff or really wet concrete. And there were also things like compressive strength after 3 months of casting. And compressive strength is, of course, important when building buildings and bridges. We don't want them to collapse. And if we give prediction about the compressive strength, we want to also know how good our model is. So there's no, at that point, any model selection or hypothesis. It's just that we need to tell for the concrete expert in which range these errors are going to be, whether they can trust this model. And we had the predictors. There were recipe, how much cement, water, additives, mixing different kinds of sand, and the end result was very successful, so that it was possible to reduce amount of natural sand a lot, and then these have been in use in Finland for a long time. Medical applications, predicting cancer recurrence, or predicting any treatment effects and so on. Again, the predictive performance of model is important. The concrete, it's very complex chemical and physical reaction going on when the concrete hardens. We are not able to model that from first principle. Same as in these medical applications. Humans are really complex. We are not modeling them starting from quantum physics. And so we are modeling very complex phenomena with models that are much simpler. So it's open anyway. And then this is decision theoretical approach in spirit of many of these Lindley, Box, Rubin, Bernardo Smith, etc. I will also in this talk mention a little bit about this continuation for Stan tutorial, how then use leave-one-out cross-validation for Stan. And overall, here's the outline for the first part. So what is cross-validation? When is cross-validation applicable? That's often asked question. How to do then fast cross-validation? Little bit about related methods, 2 slides, 3 slides. Cross-validation can be used for model comparison and selection, because if we have 2 models with different predictive performance, we should probably use the better one. But there are also alternatives, and that's the then model averaging. Don't just choose one. And then there's also the second part is about the projection inference in high-dimensional problems, and that's my recommendation then for feature selection. The kind of the story why we need or why we can benefit from cross-validation. Yes, true function, it's just now linear. And then true data generating mechanism could have then that we have the connection between x and y, that line, but then there's variation around so that if we observe new y with the same x, there's still some variation. Here's one realization of data from that process. And here's a posterior mean. And it's likely that it's not matching the truth. If you have alternative data, we could have some out of it. And that's, here's back the first data. And then, of course, we have posterior draws to describe the uncertainty that, given just the finite data, what this line might be. Giving this posterior for possible different lines and possible different variations, we can then integrate over the parameters and get the posterior predictive distribution, which would then predict what we would see in the future. And so we get it just by, you can see, integrating over the posterior theta given x and y, so all data, and then predictive distribution condition that new x is 18. And now I use this y tilde to denote some future observation compared to without tilde the observed observations. In these prediction problems, then we are interested in the predictive performance for new data. So what if we now, after we made the concrete experiment, different mixes of sand and different recipes, if we are using this model in new cases, how good predictions we will get then. But then, of course, we would like often to know this predictive performance estimate before weighting new observations. And instead of then waiting for new data, we can take one of the data points and leave it out, fit the model with the other data points, and look how that performs. So we now pick this 18th data point, leave it out, and you can see now that we have a little bit different estimate. It's specifically usual that that fit is then away from that data point. Of course, we wanted to fit to this data, so it's natural that if we then take it away, the estimate might be to some other direction. Now we could use this then from the mean to that actual point to get leave one out residual. So that would be one kind of the error for new data point. So we just compute the expectation of that, leave one out predictive distribution, and we can use then these to compute, for example, root mean square error, r squared, or in this concrete example, I reported the different quantiles for the or the kind of the distribution of errors. For example, that I could say that 90% of errors will be smaller than this. 95% of errors will be smaller than this. And this was kind of the easy then for the concrete expert to understand. There's a demo for leave one out r squared. You can find the link. In addition of using these point estimates, we can also then look at this whole predictive distribution, and we can now try to then estimate the goodness of this whole predictive distribution. And same way as we did the predictive distribution for in case when we condition on full data, now we are just using the leave one out posterior where we have left out the 18th observation, using this minus 18 then there. We can evaluate the goodness of this predictive distribution. Now this one first shows the posterior predictive density. So we are using now this full posterior predictive density, the red line. And we check that, okay, this 18th observation, what's the density for that? And of course, we would like to have high densities, usually. It would mean that we are predicting well. But you can also see, so that now we get the value from the full. And now instead, if we use the leave one out predictive distribution, we get smaller density. And this is kind of reflects that if we haven't used specific observation for fitting, we are a bit more surprised what the value for that observation is. Or when we include it, of course, it's easier than to predict that observation too. Now this was just for one point, but we can then repeat this for all points. So we repeat this leave one out process 20 times. We get 20 values. It's common then to take a logarithm of these densities. One benefit is that often these densities are quite small, or if we have many of them, going a log scale gives us benefit in the kind of the more dynamic range. There's also another benefit. I'll tell you soon. So here's the then sum of these log predictive densities. And then we call this ELPD LU, expected log predictive density. And in a way that this is the what we would expect would be the log predictive density for new data. And this is an unbiased estimate of this log posterior predictive density for new data. As a comparison, we can also compute these log predictive densities using the full posteriors. And you can see now that that has a higher value. And now thing between these are that it's an interpretation as effective number of parameters, interpretation of complexity of this model. In this case, we have 3 parameters: intercept, slope, and sigma for the noise deviation. And you can see that then this gets quite close to the 3. This is something which, however, the kind of the interpretation as effective number of parameters, it holds only asymptotically for well-behaving models where the number of parameters don't increase at the same speed as the number of observations. So there are some cases where instead of effective number of parameters, this can be used also as a diagnostic, finding out not well specified models. And that's now the ELPD LU is just a point estimate how good we think our model is for the future data. But we can also compute the error estimate for that. so we know how much uncertainty there is. And now I showed now the kind of the computations when I showed also that, okay, we could compute like these 90% error rates. For those, we would do the similar computations that we would repeat the point estimate errors for all points, and we could similarly compute these standard errors. The log score has the benefit that it estimates overall how good this predictive distribution is anywhere, the whole shape. And also it had the benefit of having the connection to this effective number of parameters. But then for application experts, it would be better to have also something which is in a scale of measurements and not in scale of log densities. Now in this example, I had chosen X so that they were equidistant intervals in the fixed, because it made the plot look better. We might have this kind of data collection mechanism that we want to make an experiment where we choose, make the design of experiment and choose which axis to use to make the measurements for Y. Or it can be fixed already by nature. These could be dates, and so they would be equidistant interval. And now this standard error for ELPD law, it's mostly about uncertainty about Y given X, but it's in a way that in leave one out, we are all the time leaving both X and Y out. But since if this is fixed, then this standard error is also about just the conditional part. Sometimes we might have that X is random, so we are just observing some population, and then we are not in control what kind of coverage. For example, in medical case, we are not controlling what kind of people are coming in. And then this includes also now the uncertainty about X in a way that we don't know also what is the future population. So we have, of course, some information now also about the distribution of X, but that when we think about uncertainty about the future performance, we have related uncertainty about the distribution of X. There could be coverage shift if we know that in the future X's are going to be different. This could be maybe if we have this kind of population dynamic model, how people are aging, we could know that in the future we have more older people and less young people in most Western countries. And then if you now use with Stan loop package, it will then have this, it tells that we've computed from 4,000 by 20 log likelihood matrix, so 4,000 is number of draws, 20 is the number of observations, and we get ELPD loop estimate and standard error for that, and then the effective number of parameters estimate and error for that. And I'll come back to the bottom part later. Okay, more different kinds of data generating mechanisms. Here's some data without, I'm not yet revealing where this comes from. Maybe we have some fit there. You might think that, okay, maybe it should be more flexible fit, but that's now not the point. But the point is that now the new data is actually there. So we have certain type of coverage shift. And this extrapolation is always much harder. And we might even know that the X is in the future. And this comes then to the question people asked, can we use cross-validation or leave one out cross-validation with time series? So the data was now this Lake Huron data set in R water level during these years. And now if we have this data, what we would be interested in is then predicting in the future how the water level is going to behave in the future. Of course, there could be some other questions to analyze also whether some interventions in the past had significant effects. Yes, we can use also leave one out cross-validation in this case. But now in this case, the circles are now the points we would leave out. But of course, it's now easier to predict that left out point if we know also the future, where it's going. But it's still telling us something about this conditional distribution. So it can be useful if we want to focus on that part. But often in time series, we would like to do this leave future out cross-validation. So we leave all the points in the future up to some point and then predict maybe one step ahead. Or sometimes we are also have that kind of, like in the electric companies, they like to predict next 24 hours. So there can be multiple steps, and for each hour to predict how much electricity they need to produce. There's also variation of this leave future out, that we leave just certain block of the future observations, and if that removed block is long enough compared to what are the dynamics of that process, we can benefit for learning the global parameters also from the later observations, but do not much harm for that one point there. Then people ask, can leave one out or other cross-validation be used with hierarchical data? And yes, in leave one out case, it's the same as in time series. If we are interested in these conditionals, that what if we would have just one observation missing there, how well that conditional distribution can describe the variation there. But there might be also other types we are interested in. Maybe we are here also interested in this age. Maybe we want to predict one step ahead, leave future out, how well it can predict that. Or maybe we are interested in leaving observation from all rats. Here, this is the rat age and weight. Leave all the points at some age. Or we would like to maybe leave one rat out. And then these different types would focus on different properties of the model. Sometimes they focus then on how the model is in time or how the model is now over different rats. Maybe we are interested in how well we can predict the growth curve given just the initial weight. That would be maybe quite logical application that instead of rats, this is what we also do for human babies. If given initial weight, we make already predictions, or we do also the kind of the leave future out one predictions, but predict usually the adult height, for example. So all in these cases, when you want to estimate how good predictions you get from your model, you have to think about this data generating mechanism, and you have to make some assumptions about that. It's possible then that sometimes you have different assumptions in your model. You might sometimes have simpler model, but then you would want to test that is this simple model enough if I have kind of less assumptions about the data generating mechanism, and then cross-validation is good there. Also, you should use the knowledge of the prediction task if available, in a way that are you doing just one step or m step ahead, or what kind of group you want to remove. And then sometimes it's also that you can focus on different parts of the model, even if that would, you are not going to use this specifically for predicting future. Richard McElrath is doing these anthropological studies. It's unlikely that there would be repeated experiment for an ancient civilization recreated, but it's still possible that if he uses hierarchical models for different civilizations, he could then look at different components of the hierarchical model by thinking about how these different options I mentioned. Okay, leave and out cross-validation, we need to get this posterior distribution for data where we have left one point out, and if we have a lot of observations, then it could be costly. But then we can use this Pareto smoothed importance sampling I describe soon, or k-fold cross-validation to make this faster. Here's again this simple data I showed you in the beginning. We have posterior draws and the posterior predictive distribution, and now so the lines have been drawn so that we have these posterior draws theta s from the full posterior, and we can then approximate that posterior predictive distribution, and now it's missing divided by s, so it should be mean from those samples. And then that way we could also then evaluate what's the predictive density for that point. But now if we leave that out, we can still use the same posterior draws theta s, and you can see the difference. These are same draws. Only thing I did, I changed the alpha value. And if the alpha value goes to 0, the line gets completely transparent and you can't see it. And how I changed the alpha is based on these importance sampling weights. So we can compute this weight so that we have the theta s, and we are able to evaluate the posterior density based on the full data and posterior density of the leave and out data. But now this is we didn't need to do MCMC. We have already theta s, and so we just evaluate that with that leave and out data. And the nice thing is that for likelihoods with factorize, this ratio is then proportional to 1 per the likelihood evaluated with this theta s, one draw from the posterior. So it's easy to compute. We often take logarithm or work in the log scale, and then I'll later on show stand code for computing this log-lick. And then we can get the live and out predictive distribution. And so now the density for the left out observation given the live and out posterior. So we are using the full data draws, the predictive distribution, but now we are just weighting them. Now there's a change. I went from R, the raw ratios, to W weights, because we additionally do Pareto smoothing of the weights, and I will mention about that soon more, but it helps to stabilize this importance sampling. Here are now 400 importance weights for leave that 18th observation out. And you can see that there's a lot of variation. Some of the weights are much larger. You can see I also, for reference, the red dashed line shows what would be if, with the equal weights. But even if there is now this variation, we have a good situation that it's not that one weight would be having just a weight 1, but there's still enough variation. Here's the same now with all 4,000. So I've showed you first just 400 because now it's a bit more difficult to see the small, very small blue bars, but the largest value is there around 0.02, so much higher than what would be with equal weights. We've seen already this week a couple times the equation for computing the effective sample size for importance sampling and using the variance-based estimate. Now, this is now including also the effective sample size computation for Markov chain, because we got the draws from Markov chain, so we need to do both taking into account dependency in Markov chain, which reduces the effective sample size, and then here you can think that if we would have just one weight, which would be 1, then we would have just one effective sample. And on the other hand, if the all weights would be equal, then we would have 4,000, if we would have, of course, independent draws from the posterior. And then this is something between, which relates then to what's this distribution of weights. The reason why this, so the importance sampling leave and out was proposed by Hennenfent in beginning of 1990s, and there were several papers by others also analyzing then the properties. But the problem was that it's possible that the distribution of the ratios has infinite variance. If it has infinite variance, the effective sample size based on variance estimate would be then 1, and there's no kind of the good what would be the convergence? There's no central limit theorem doesn't hold anymore. And then what we did now is that we make a generalized Pareto distribution fit to the tail of this distribution. And the good thing is that then that the generalized Pareto distribution has a parameter k, which tells about how many finite moments we have. It turns out that if we in addition do some, we can also use that Pareto fit then to smooth those weights, or we can say that we are modeling them weights. So it's same thing as in eddy modeling, that we can reduce noise by adding model. Theory says that most distributions, if we go far enough in a tail, can be well approximated with this Pareto distribution, and then we can use that as a model for the tail, and then we can reduce the variance. And it turns out that we can manage, even if the variance of the row ratios would be infinite, our estimate has finite variance, and we can get to up to k around 0.7. And there's also both empirical and theoretical justification for this value. Some results are there, and then you can find the references, also the longer paper on Pareto smoothed impedance sampling. If you use tan or the loop packets, you will get these. You can plot these kind of diagnostics, the Pareto K for each observation. You can see in this case everything's fine. This Pareto K is also useful as an influence diagnostic, because we get more variation in these impedance ratios if the full posterior and leave-on-out posterior are very different. And if they are very different, it means that one observation was very influential. And we often see cases where if we get these Pareto Ks larger than 0.7, that it was actually misspecified model, not taking in outliers or having some other problem. And then the loop package then reports these Pareto K diagnostics. So as a summary, how many of the K values are in which range, good, okay, bad, very bad, and the minimum effective sample sizes for each group. So we get a reliable result, and here you can see also these effective sample sizes looking good. And then what we can do if we have only few number of observations where this Pareto K is large, we can run MC only for those observations, or if we have many, we can use k-fold cross-validation, or we then should fix the model if we have a lot of these very bad k values. So this was the for the row ratios, and then in generated quantities. So here in the model part you can see y distributed as a normal, and in generated quantities currently we can't vectorize this, so we need that for loop, and then we compute these normal LPDFs, and we get that log likelihood matrix loop package can use. And then these rstanarm BRMS packages compute this also by default, so easy to use loop. The limitations of this Pareto-smoothed impedance sampling, if we have hierarchical model, we sometimes are interested in analyzing the goodness of that hierarchical model, or even our prediction task be such that we want to predict for a new group, and then we would like to leave one group out. Cross-validation, that's challenging for impedance sampling because we are then removing many observations, and more observations we remove, more different the full posterior and leave one out posterior are, and then it's more likely that we get really bad distribution for these ratios, and then this Merkel-Pur-Rabe-Hesketh, they saw one example that how then using quadrature integration we can perform better. Quadrature integration and then possibly impedance sampling combined. I mentioned that this is very easy for cases where the likelihood factorizes, but we have also case study and preprint on for non-factorizable models. So especially if the likelihood is multivariate Gaussian, even if it's not non-factorizable, we can do this. For time series, we can do approximate leave future out cross-validation. There's also case study and soon preprint. So the same data, we fit now AR2 model. We can do the same thing, just start removing from the end observations. So we are leaving more and more future out, and then given those points which we still have, predict the next. And this is what happens with the Pareto K when we remove more and more observations. Eventually the Pareto K goes very high, and so we know that, okay, like some tens of years we can manage, but then it fails. But we can do some repeats. So those at the circle points, we run MC given data up to that point. Then we can continue with impedance sampling, removing observations only by impedance sampling, and then again when the Pareto K goes too high, we repeat, and so on. And you can see that overall we did not need to do MC for all combinations. In k-fold cross-validation, we divide the data, for example, in 10 pieces, and then we would need to do MC only 10 times. We can use it to approximate leave one out. We can use it to, it's especially good for this leave one group out, or we can do also that if we divide it in just 10 parts, and if we have more than 10 groups, we can remove more groups at the same time, and can be used for time series with leave block out, although they are, it's more difficult there. So this is how it would look like if we would do balanced k-fold approximation of leave one out. We would preferably have, so we are leaving several observations at the same time, but we would prefer them to be far away from each other so that locally they still have the same amount of kind of the information from neighbors. And then we would repeat this by taking next ones and then the next ones and next ones, and then we could loop this 10 times over. And then we could proceed as if we would have been doing leave one out, but no need for the impedance correction. if we do just a random k-fold approximation, we have possibility that we sometimes then get observations removed which are very close to each other, and then we go more to extrapolation, and then that's why the balancing might be useful. Here's the hierarchical example with rats. We can do approximation of leave one out, or leave one rat out, or then we could leave several rats out at the same time. And the loop package has then these helper functions to generate indices sets, how you can divide the data, and there are some examples how then to modify your code to if you use k-fold cross-validation. What is widely applicable information criterion, or Watanabe-Akaike information criterion? So Watanabe wrote papers showing asymptotic consistency of WAIC and Bayesian cross-validation overall, not just the important sampling version, but overall the Bayesian cross-validation. Then this was also then the first truly Bayesian information criterion, but it has the same assumptions as leave one out cross-validation. So if you ask, can I use leave one out cross-validation here? And if the answer is no, you should not then use WAIC. It has the same assumptions. It's just not based on experiments. Sysloo is more accurate, but more importantly, it has much better diagnostics. So it's easier to find out when it fails. If Sysloo fails, in those same cases, WAIC will also give you wrong answer. But it's just more difficult to diagnose that situation when it gives wrong answer. So there's no need to use WAIC because there's the computational same cost also. I think that then it's also better to use leave one out cross-validation, because then if you are thinking about cross-validation and this that you are predicting one next observation, it's easier than to think that what's then if we want to predict, the prediction task is somehow different and how then modify. While for the information criterion, that's a bit more complicated. It's also often these information criterion are multiplied by -2. It's goes back to time people using Gaussian likelihood, and there you then get rid of that -2, but it doesn't give any benefit for interpretation. Howard mentioned DIC. AIC uses maximum likelihood estimate for prediction, but you don't want to make predictions with that. DIC uses posterior mean. You don't want to use just the posterior mean, you want to integrate over the posterior and use the posterior predictive distribution. BIC is something different, and then there's of course many others. But WAIC is the only information criterion measuring if you would use the posterior predictive distribution, but then it's same as LU, and then, as I said, LU has the benefits in computation and diagnostic. Marginal likelihood Bayes factor has been mentioned this week. It's like leave future out one step ahead cross-validation, but starting with 0 observations. In previous examples, when I had the leave future out, we stopped at some point so that we also always assume that we have at least some amount of data to make predictions. Because like for the Lake Huron, we don't want to consider that kind of case that how well we could predict the next year water level if we use just the prior. Of course, we want to use what we've learned also from data, and then that's why we had always at least some data to make predictions. And so for the Lake Huron, it would look like this. So starting with no data, and then we would have a difficulty how we predict that first observation, which means that it's very sensitive to prior, even if the posterior is not. It's also, the Bayes factor can be unstable in case of misspecified models. That would be worth of another half an hour talk. I'll just show some examples later. And unfortunately, this is also asymptotically. So even if we get more and more data, if all models are misspecified, we get, in the worst case, we get this kind of flip-flopping between models and very unstable behavior. But so far, I've mainly talked about that we have just one model. And that's already the very important part, that where cross-validation should be used when we are just telling whether this model is useful for making future predictions. We don't need to compare to anything else. If I tell to concrete expert that 90% of errors will be less than this when predicting compressive strength, they immediately have an idea that whether that's useful or not compared to what are the safety limits overall when building bridges for compressive strength. Same thing for if we are looking at the treatment effects, it's also we can look at whether we can predict the treatment effects with the reasonable accuracy. It's also useful in model checking in similar way as posterior predictive checking. I mentioned Tuesday. I did mention now that this Pareto K can be also used as diagnostic to find influential observations, outliers, or then that it's misspecified model which should have a thicker tails, for example. That effective number of parameters in badly misspecified models, we see that this p-lu estimate can be larger than the total number of parameters in your model. And then it's again one indication that now you should fix your model. We can look calibration of leave and out predictive posteriors, which improves based on looking at just the posterior predictive, because if we don't do the cross-validation part, we are using data twice in that way that we get too optimistic results, and they are demos in that web address. Sometimes cross-validation is not needed. If you do posterior predictive checking, it's often sufficient. Example is predicting the yields of mesquite bushes. On the left-hand side, the black line is the density estimate for data, and then the gray lines are density estimates for replicated data from the model. And we already see that that's not good model, and we don't need to run cross-validation to say that, okay, let's don't use that model. And there are the pointers for the posterior predictive checking, and so that's something you should do anyway, because that gives you more information what to fix than what the cross-validation usually tells. But we can do also model comparison. This is from Statistical Rethinking by Richard McElrath. Hypothesis that primates with larger brains produce more energetic milk so that brains can grow quickly. And then there's these two models. The neocortex the neocortex, now I can't remember what was the exact measurement, and then the log mass. The main point I chose this very small data example here was to show that when we had these ELPD Lu estimates for two models, when we do the comparison, we should do it point-wise, because some observations might be really difficult to predict for both models, and then it's better to look at this comparison pairwise, that how well, what's the difference predicting one data point we left out. And so here we have the individual log predictive densities for model 1 versus model 2. We could then have the summaries. So we see that there is difference within these ELPD Lu values. But we can't use now in the comparison these standard errors directly. Instead, we take these pairs and we compute the differences, and then we compute the standard error for the difference. Now we see that there's not much difference in predictive performance. The more complex model gives better predictions, but there's a lot of uncertainty, which is natural now because there's so small data that it's difficult to make difference between models. Again, sometimes we don't need to do this, like here. It's clear that modeling that yield of mesquite bushes in log scale is much better, and we don't need to know that log predictive density in this case to say that we should favor the second model. For simple cases, you may assume that true model is included. This simple case means that our data collection process has been such that that in a way what we are able to model is such simple that we can then assume also that one of our models would be true model or very, very close to true model. And then there's, in that case, we could also do predictive model selection. So there's the San Martin and Spezza-Ferri. Using the same idea that we want to know what's the future performance, and then how to do it if we assume that one of the models is the true one. For these very simple cases where you could assume that true model is included, I just want to say that you should not force your design of experiment or analysis to stay in simplified world. So you should design the experiments so that you collect all possible information which is then of course economically feasible and so on. Or if you have data, don't throw away part of that just to make your model easier. This is a big problem in medicine, that studies are designed so that you have just two groups, even if you could have, for example, for medicines, you could have different dosages tested at the same time. I've also been involved in analyzing such data, and it seems terrible that start a drug experiment with placebo and some dosage, then have a treatment for 1 year, then follow up 5 years, write a paper and wait till it gets published, and you spend 8 years, and then you start experimenting. What if we instead compare 1 year treatment or 3 year treatment? Repeat. What if we compare 1 year and 5 year treatment and repeat? While we could do this all the time continuously, as soon as some stopped and we could see much earlier these effects. So that's why I think that in many cases we should aim at kind of the models that we unfortunately then are going to be outside also of this M-closed. It is also possible that if we have a fully non-parametric model, that it is possible to have such fully non-parametric models that the true model is also included. And then this is related to what Chris Holmes talked earlier this week, and there are some other papers. But this is not commonly done, because the posterior convergence rate can be slow for these kind of fully non-parametric models, and that's why we want to use more informative model assumptions and prior assumptions to get more quickly something useful out from small data. If we have nested model case, it's often easier and more accurate to analyze the posterior distribution of more complex model directly. In this primate milk example, we could just use that second model and just look at the posterior for these coefficients. No need to compare to that simpler model. In that primate milk example, there was also that there wasn't clear decision. The more complex model had slightly higher log predictive density, expected log predictive density, but then the standard error was that big that it wasn't clear. Maybe continuous expansion including all models. Well, in that specific case, that model would be the bigger model. It includes also the smaller model as continuous special case. And then we could analyze the posterior distribution directly. That case study there shows example for the beta blockers. You had that example in on Stan tutorial on Tuesday, and it shows that also if we are looking for is there effect or not, looking at the posterior distribution gives us in a simulation study, it gives us we can detect smaller effects if we look at the posterior than if we use cross-validation. Cross-validation has and the benefit comes from that if we can trust our model assumptions, we can detect smaller effects because we get the additional benefit from the model, reduced variance. While cross-validation has that assumption that we don't trust our model and we are predicting the future data distribution kind of non-parametrically, and then that's why it has higher variance. Instead of trying to do variable selection, just include all variables. If you assume that only small number of those variables are relevant, use sparse priors like regularized Horseshoe. Or if we can't do the continuous expansion, maybe we can do model averaging with usual Bayesian model averaging or Bayesian stacking. I have soon some examples showing that yes, it's beneficial to do averaging instead of selecting. In a nested case, we might end up, so in this case that we see that the predictive performance is similar, we might end up then choosing simpler one if there's additional cost for extra parts. But for the predictions, I would say that I would prefer usually the more complex model. Because then we are taking into account the uncertainties. If I'm uncertain whether I should include this or not, Bayes' theorem says include it and integrate over that uncertainty what is there. So one option then to do model averaging, so this was recently published in Bayesian analysis. We consider the model averaging as a decision problem with aim of maximizing the predictive performance. So I've already talked a lot about, we want to know how good these models are, but then we could also think that when we have several models, how to combine them to maximize that predictive performance. We have some scoring rule S, not yet defined. We have some weights, WK, and K is then the indicator for model, and MK refers that what model. We have the predictive distributions for future data, Y tilde, given then the posterior for each model, and then we would like to know what are these WKs which would give us best predictive performance, and the score is comparing that model average to true future data distribution, but then we don't know that, so we approximate with leave one out, and then we can define stacking weights, a solution to this optimization problem. So we have the scoring rule, and then we have this leave one out predictive densities and the weights, and then what are the weights that would maximize then the combination of the leave one out predictions. Then the combined predictive density would be like this. And when we use log score, we call this stacking of predictive distributions. And now there's the, we get log of weighted average of predictive densities. And then nice thing is that then these leave one out things we can again approximate with sysloo. Other cross-validation structures could be used if you want to do averaging for some other prediction task. Here's a very simple toy example. We have true data is just coming from normal distribution with mean 3.4 and standard deviation 1. But then for simplified illustration, so here's the true value is here, 3.4, but now we allow models only at 3, 4, 5, 6, 2, 1, just on these discrete values. Of course, we can see now that none of them can fit exactly to this, and we know what's also discussed previously this week that it will, we just look at the posterior probabilities of the models. The posterior probability for model 3 will go to 1, and it will use then the predictive distribution for model averaging would be then also just based on this 3. Here are now the model average predictive densities, and amount of data increasing, and if we look at here 200 observations, this is now the Bayesian model average, and since now the all probability mass is for model 3, it's a bit off from where it should be. You can skip the middle line, and then this is now the stacking solution, and it has now non-zero weights for models 3 and 4, and it's able to get average of those which fits there. Of course, in this case, we would prefer continuous expansion and make a model continuous expansion with continuous variable. That would be more sensible than do the discrete model averaging. But this is the simplest case where we can show the kind of the difference that with the stacking, it's possible to, if we had discrete models, also go between models. Here's then the predictive performance when the sample size grows. Red is stacking of predictive distribution. First one is the log predictive density. The green is BMA, and you can ignore blue one. So for the log predictive density, stacking performs better than BMA. For mean square error, stacking performs better than BMA. Useful thing is also now that one of the problems with this Bayesian model averaging, which has been known, is also so-called prior dilution. What if you have several similar models? How you should share your prior between several similar models? And this happens easily when you have a lot of covariates. If you add similar covariates, you will get combinatorial explosion of similar models. In this case, we demonstrate this effect only by adding copies of model n for 1, and more of these copies we have, the worse the BMA performance is, because, and this is now with fixed number of observations, but more copies of this model gives more prior mass for this, and so it's also in model averaging using more and more this model. While stacking doesn't care about that, it can share the weight between these, because it still only matters what's the average combination of the predictive distributions, that it's good. Another example, we have a linear model. So there's 15 covariates, 15 coefficients. It doesn't now really matter what the coefficients are, but they are all non-zero. First, we have non-nested open case. So we have only, each model has only one covariate. Again, bit of artificial example. And now in the same way, we can think that now in a Bayesian model average, when we get more and more observations, it will assign at some point probability mass 1 to just one of these models, while stacking can share the weights between these models. In all these plots, the curves are exactly the same. It's only that we've highlighted one of the curves. So in a plot A, we've highlighted with red stacking, best log predictive performance. Here it's BMA, lower performance. And here we have also model selection by leave-on-out cross-validation, red, and Bayes factor or marginal likelihood with blue. And you can see that even if this is all models are misspecified, also it's better not to select the highest probability model. We still have benefit of averaging, so it's not yet converged to that there would be just weight 1 for one model, although these are getting closer because it's getting more and more mass to one of the models. But then stacking performs here better. Well, we have also M-closed case, so a series of models which have 1 by 1 more coverage. And so the true model is then the 15th model, including all the coverage. Here, again, stacking with red, highest curve. Now, even if we are in M-closed and the true model is included, BMA is working badly. And the reason is now that this prior sensitivity, we have used quite WAIC prior, and so it's penalizing complexity a lot, and so it is selecting too simple model. And this is, of course, we could say that why we then didn't choose better priors, but that's the problem when we have complex models that the result can be sensitive to how wide or narrow prior we choose. And we didn't get that sensitivity here. In model selection now, so now there's no difference between model averaging and marginal likelihood, leave-on-out. Selection is surprisingly working quite well. We can use stacking also to combine inference in multimodal case. Here's an example that true posterior distribution is multimodal. Variational inference using unimodal Gaussian distribution can fit only one of the modes, but if we have different initial values, some of the optimization ends up here, some of end here, and then we stack predictive distribution, and so we can also do that. So in open case works better than BMA. In M-closed case can have better small sample performance than BMA. But there are also cases then it is possible that then that the BMA works at least as well. The Bayesian stacking, I recommend not to use it for model selection. Of course, you may drop models with chair weights, but you should not choose the model with largest weight unless that weight is 1. Otherwise, you should then integrate over or consider continuous expansion of one of those models. So we can use cross-validation for model selection if we have a small number of models and the difference between models is clear. You should not use cross-validation to choose from a large set of models because that selection process itself leads to overfitting. I'll show you examples. Of course, this overfitting in selection process, it's not unique for cross-validation. It happens also with other criterion, also including marginal likelihood. We can use term also selection-induced bias, or then the selection, the overfitting in selection process. This is something for cross-validation that was recognized already in these early cross-validation papers, for example, by Stone, but largely ignored. Every now and then someone writes a paper showing this, and then for some reason people tend to forget this. We could estimate the performance of this selection process itself using two-level cross-validation, but it doesn't help choosing better models. And then this gets all the time more dangerous when we have more and more models, and then covariate selection is one of these examples. Here's an example. Start with the 20 observations. We have 50 covariates. We have full model including all covariates and sensible prior dashed line. We start from the full model. We remove we compute cross-validation estimate for all models with one less covariate. Choose that model which has the best estimated performance and repeat. So we are doing backward selection using cross-validation as a criterion to choose the best model. This blue dashed dot line is how good the cross-validation thinks, how good models it's finding, and it thinks that it's finding even better models than the full model, and the black line is then with independent test data. And you can see that it's actually getting worse. We get slightly less problem when the amount of data increases. You can see the scale also here is changing on the y-axis scale. But we have this problem. We can't use cross-validation directly for variable selection. Here's 100 covariates, 100, 200, and 400 observations. Cross-validation, WAIC, DIC, marginal posterior probabilities. I'm not showing the map estimate or the kind of the most likely model estimate. It would be worse than here. Based on when we go through the models in order of the marginal posterior probabilities. And you can see this is better than cross-validation, but it's still there's a problem. And for all these, it gets better when we have more data. I'll come back to this last case, which looks much better. And here's also, because these were averages, the black lines were averages of many simulated data, and the gray lines now show that we have a lot of variance in these different approaches, which cause also problems. And then with different real data, same thing, and you can find these in the paper. Okay, first part is over. It's good to think prediction of observables, because observables are the only ones we can observe in a way that it's only toy problems where you can later get the answer that what was the true parameter value. But even in the real world, there are many cases where you can make more observations, and you then can compare your model predictions to new observations, and that's something that you can then really check that compare to. And we can use cross-validation then to simulate this, predicting and then observing new data. It's good if you don't trust your model, because in a way that the cross-validation is reusing the data, but it's reusing this without model assumptions. They are kind of pseudo Monte Carlo samples from the future data distribution. You can still include information about the structure of the data generating mechanism in a way that whether you are leaving one group away or whether you are leaving all future observations away and so on. But you are not adding other model assumptions there. And so different variants are useful in different scenarios. And it has high variance, and which has the effect in, especially in model comparison, and especially if we have many. And if you trust your model, you can beat cross-validation in accuracy for predictive performance estimate and selection. Okay, then I'll go to part 2, but before that, let's have a little break so that stand up. I want you to be awake, yeah? And stretch a little bit. And then one leg, another leg. Oh, feels good. Let's do a bit of running. Let's get blood flowing. Yeah? And a couple times go down and up. And then a little bit shaking of hands and legs and breathe. Okay, now you can sit down. Because I know 2 hours is a long time to sit, and I want you now to wake up again for the second part. Projective inference in high-dimensional problems. So since we noticed that we can't use cross-validation in this high-dimensional feature selection, we had to figure out something else. When I now say high-dimensional data, the examples number of features is from 1,500 to 22,000. Number of observations is really small compared to that. We could scale this to bigger N and bigger P also. But these are now the examples. For this kind of data where we have much more unknowns than observations, priors are really important. We can use shrinkage priors, hierarchical shrinkage priors, dimension reduction. So the shrinkage priors, especially if we assume that many of the features are irrelevant. Dimension reduction if we assume that most of them are relevant, but there are a lot of correlations. And with these priors, then we can make useful inference. We use two-stage approach. So the first part is just construct best predictive model you can. Use all the available prior information, include all the features, do model checking, use posterior predictive checking, use cross-validation and everything so that you're happy with this best predictive model you can make. And after that, it's separate. So this part is about the information. We are including what we know there. And then we use Bayes' theorem, which says that we then need to integrate over the uncertainties, over all the uncertainties. We should not throw away anything. And the second part is decision process. Given this, we've included all the information. Can we make such decisions that in the future we don't use some of the features? And if we don't use some of the features in the future, how we make the inference, taking into account all we knew already. So I already said that we want this rich model, and if we care only about the predictive performance, there's no need for feature selection. Just make the predictions if you are happy with the model. So we might sometimes need to reduce measurement or computation costs in the future, or we want to improve explainability. It's possible to get some insight about data, the phenomenon, if we can say that, hey, here's this small set of variables which can give you good predictions. There's the rest of the variables which give you maybe a little bit additional predictive performance, but these are the most useful ones. And we have two options here then, that find a minimal subset of features that yield good predictive performance, or find all features that have some predictive information. I focus now on this minimal subset, but then it's easy to extend to this second case by finding the minimal subset, remove then, and repeat. And then we can find all which have some information. I briefly advertised our work on regularized Horseshoe prior as one of the useful shrinkage priors. So there was a previously Horseshoe prior. It can be seen as continuous version of spike and slap. In here, the figures, this is kappa is shrinkage factor, and we can look at what is our prior distribution for shrinkage factor. Shrinkage 1 means that we shrink completely to 0. Shrinkage 0 means that we don't shrink at all. Spike and slap with point mass at 0 would have then point mass for shrinkage, full shrinkage. And if the slap would have infinite width slap, we would have then point mass for the shrinkage, no shrinkage at all. Horseshoe is continuous, and it's possible to have a lot of mass here for no shrinkage and a lot of shrinkage. And so it's possible that the prior says that we are likely to have separate relevant and non-relevant, but also something between. The benefit also for going to continuous version is that now this works with Stan, and then we get the benefit of Hamiltonian Monte Carlo, gradients, and so on. The problem with this was that no shrinkage allows complete separation in logistic model, and then you get problems, and then regularized Horseshoe at additional finite width slap. So we can move, so this is again, these bars are for spike and slap, where there would be finite width slap, and then we can have a corresponding regularized Horseshoe version, still having the separation to relevant and non-relevant, but we can get some regularization for all relevant ones too. And there's the paper explaining and also explaining how to set the prior parameters based on your sparsity assumption. So if you have a guess how many relevant features you would have. This advertising regularized Horseshoe relates to that. Also this week we've seen spike and slap, inference, but then shrinkage priors alone do not solve the variable selection problem. Although it is common, there are a lot of papers doing fit model with shrinkage prior and then select variables based on marginal posteriors. If it's this kind of discrete spike and slap, you could look at the marginal posterior probabilities. In continuous cases, you could look at the whether your posterior is overlapping 0 and things like that. But this is difficult for correlated features. Another thing is also that after you've chosen one of the models, it's typical that the inference is made then conditioning that some of the features are, the coefficients are set to 0, and we completely ignore what was the posterior uncertainty for those, and condition only that, hey, what we would do if we have this. And now we have the problem that we had the selection process to going there and then throwing away that information we had about the features we remove. Here's an example about the problem of the looking at the marginals. We have some latent feature, and Y are noisy observations from this latent feature. In addition, we observe, we have xj. We have total of 50 features, and 25 of them are correlated with that latent feature, and of course then correlated with each other. But they all are, these 25, they are predictive about Y. And then we have 25 completely irrelevant random noise features. We generate datasets, 50 observations. We set the correlation to 0.8, and then make inference. Here's a plot with using Gaussian prior, marginal posterior distribution for coefficients with 50% and 90% intervals, and all 90% intervals are overlapping 0. So based on the marginals, we would say that there's nothing interesting to see here. Shrinkage prior, it should help us in a way that it would make some of the coverage go shrink to 0, and then the relevance should show better. But because we had 25 correlating variables, there's a still overlap. It still seems there's not much to see there. Posterior inclusion probabilities, so these marginal posterior probabilities. There's one going over 50% probability that it should be included. This is all because when they are highly correlating, we can manage with smaller set of features than all. Here's another view what happens. Just two relevant variables. Gaussian, Horseshoe prior. The marginals are overlapping 0, but jointly it is far away from 0. But when we have more and more variables, also it doesn't help look at these bivariate marginals, because then also the bivariate marginals start to overlap 0. And it's difficult now to look this in 25-dimensional space, whether it's away from 0. So that's why then we want to focus on predictive performance. So we can use these shrinkage priors, spike and slap, dimensional reduction methods, anything to make this a nice model, and then do the decision theoretical part, find out what's relevant there. The next example shows what's the benefit of using this reference model, the good model we've already built. And then instead of looking at the marginals, find the minimal subset which has almost the same predictive performance as the reference model. So here's the benefit of the reference model. Now without the reference model first. We have the same data generating mechanism. We have 30 observations. Now we have 500 features. 150 are relevant. And here's the correlation between the relevant ones. Here, there's a sample correlation with Y. So this here, it's the absolute value of the sample correlation. And you can see that it's varying from 0 to a little bit over 0.6. The blue ones are all those irrelevant features, and red ones are the relevant ones. And we can see that irrelevant ones get, on average, smaller sample correlation, and relevant one gets, on average, higher. But there's a lot of overlap. If we would then make a decision here, if we would exclude all irrelevant ones, we would miss also a lot of relevant ones, or if we include all relevant ones, we would include a lot of irrelevant ones. So we have a problem with the noise there. Here, x-axis is still the same, and same overlap. Y-axis is now correlation with true latent function. So if we would know the true latent function, it would be much easier to separate relevant ones and irrelevant ones. But we don't know this, or usually we don't know. We need, but we can make a model for that. So by using all these 500 features, and now we are using just linear regression fit with 3 supervised principal components. I will mention about this soon more. And these are mean from the model. And we get almost the same figure. So using the reference model to remove the noise in observations, we get less variance when we look at the relevance of the features. So in this case, when we knew that we have a lot of relevant variables, it's good to have this kind of factor analyzed modality, the principal component model. But in addition, because we knew there's also irrelevant ones, the supervised part is good. So this paper describes the iterative version. So the supervised principal components is earlier idea than ours. It just is such that when forming the principal components, it does pre-screening using only features which have high enough correlation with data, and then doing the principal component part. So in that way, the principal components are the kind of the not explaining the irrelevant noise part, but more about the what is can explain. Okay, so we've seen that using any good reference model helps. The projection part, it's model simplification technique. We replace full posterior distribution with some constrained distribution Q, so that the predictive distribution changes as little as possible. So you know that we get the posterior predictive distribution by integrating over the posterior, and usually then we would use full, but now we change it with some constraint. Example constraints could be that this Q can have only point mass at some theta 0. What would be the optimal point estimates? Or the constraint could be some features must have exactly 0 regression coefficient. And so which features can be discarded? There's a Lindley 1968 paper where he considered this problem that what if you have a lot of features, but in the features you have only some of those features available. So then you would make a prediction by setting some of the coefficients to 0, but how you would then make the inference with the remaining features when you had the information in the full model. There are many papers then following these ideas of Lindley, but I want to specifically mention then this Christian Robert and his students papers which introduced this draw-by-draw projection I soon illustrate, which is also an important part of our approach. And then in our recent paper, we describe all the advances, how we can make this faster and more practical to work. Illustration of projection. Here's just a logistic regression with just 2 features. And so on the left-hand side, we have posterior distribution coefficient beta 1, coefficient beta 2, draws from the posterior. Here are predictions, so features x1 and x2, 2 classes of observations, and contours of predicted class probability. So high probability for class green, high probability for class red. And now we can ask, what is that some constraint estimate that would give as similar prediction as possible? Point estimate says that, okay, this point estimate gives as similar predictive distribution as the full posterior. We can have also then the additional constraint, what's the best point estimate given that we have a constraint that B1 has to be 0, or that B2 has to be 0. And of course, then if we are doing variable selection, we could compare which one of these solutions is closer to the full posterior, or full predictive distribution. Or we can also, so the actual projection of full posterior, so that we would use that Keil divergence between these predictive distributions is computationally infeasible. And then the draw-by-draw solves it by changing the order of the integration and optimization. And it turns out that it doesn't matter much. So it works well. And we project one draw at a time. So for each draw, we take that, what is the corresponding constraint point, and then repeat it. And then we get the projected distribution. And it turns out that then it's better to do the projected distribution than just the project to one point estimate. And then alternative constraint, and then again we would compare whether it's better to constrain B1 or B2 to B0. And then, of course, then we would also need to check out that whether that constraint is changing the predictions too much. So if we would prefer then to keep using the full model. Nice thing about this projection is that the prior is also projected. We don't need to define priors for submodels separately. So it just was enough that we were able to build this rich model once. It's good that even if we constrain some coefficients to be 0, the predictive inference is conditioned on the information related to features which were in the reference model. So we are drawing less information away. How to select then a feature combination? So how we choose which coefficients are constrained to 0. For a given model size, we just choose the feature combination with minimal projective loss. We use search heuristics because often we would have that combinatorial explosion. It's not possible to go through all models. some people have used Monte Carlo search, so it would travel around that space. But we found that we get really good results also with forward search. It has a benefit that quite often it's only small proportion of features we need to get the full performance, and then we can stop quite early that search process. That forward search is still, if we have many models, it still requires doing many projections. And even faster for these cases where we have really large P, we can use the idea from Lasso. We can add, instead of having strict constraint to set coefficient to 0, we can do L1 penalized projection. And then it turns out that we can use the same Lasso algorithms, which are very fast finding the path through the model space. That one by one switching feature coefficients to 0. And then when we have this search path, we can use cross-validation to select the appropriate model size. And again, this Pareto smoothed importance sampling is beneficial. We can do, when we do that projection, we use these importance weights to affect that projection and the criterion, and then we have different search paths given different importance weights, given different observation left out. And then we can also cache results so that if the search paths go through the same models in some parts, we don't recompute, and we get really fast cross-validation over possible search paths. Same simulated regression data as before, that one with 500, where 150 relevant ones. The reference model result is here. And in a projection, we assume that we are not able to beat this reference model, that we have good reference model. Lasso path can't manage to the reference model result, and we are not surprised because this Bayes wins again. For Lasso, it's known that when we make the penalization stronger and stronger and we get smaller models, it is also penalizing the remaining coefficients, which makes the performance to deteriorate. And there's a relaxed Lasso also, that after finding some subset, refit the model with much less regularization. And you can see now there's a problem that if not penalizing enough, the performance deteriorates. But possible to find here something smaller than Lasso, but not better performance. And projection. No surprise. So that it goes below the reference model, it's not kind of the practically relevant difference. But yes, we get better performance. So with the here, better performance with small model or slightly better, we get the same level as the full big model, including all the information. This was for mean squared error, so lower better, log predictive density, higher better, and even bigger difference there. These are quite small to read. You can check the paper, but the main point is here are different N, different P real data, in the end average. The dashed line is the reference model, which was now supervised principal components and then Bayesian logistic regression. The blue ones are projections, and they are different kind of rules to choose the model size, and usually then these third and fourth things are the slightly bigger but the better predictive performance. They are lasso, elastic net, rich regression, MLPD, classification accuracy. But overall, in a way that tuning the parameters we can get from all of these about the similar performance in log predictive density or classification accuracy. But then we have huge difference in number of features. This is in log scale. It's probably difficult to see, but here, this is 1 feature, 10 features, 100, 1,000, 10,000. The blue ones, much, much better. The glioma has this 22,000 observation at the features. Our reference model is using 1,000 of those features. Lasso, elastic net they are going also smaller. Here this projection which gives good classification accuracy here, it's using less than 10. So we went from here to less than 10. So is this computationally costly? It's not that bad. Our code is not fully optimized, it's R code. Part of it is using also code, we can use some code from also GLMNet, but not all. So this Lasso 2 is now the Lasso from GLMNet, which is highly optimized. As a comparison in a way that how much it's just the implementation difference that our doing the same Lasso thing with GLMNet code or our own code is slower, which can then explain also part of the slowness here. So the projection is here the seconds and the time to form these reference models are here. These are quite good compared to if you would do shrinkage prior, spike and slab prior inference for this kind of data. I showed you before these figures, so when kind of comparing to the previous, I showed compared to Lasso, but here's also compared to marginal posterior probabilities. And the last line was using the reference model, was actually spike and slab model. That's why it says here BMA. And then we got much better with the projection. Same with the different real data sets, much better. Sometimes even here we get difference in a way that we need that. So this is not taking into account yet the new cross-validation over search paths. So it's still overestimate how good it is. But with the new cross-validation over search paths, we get that also much better estimate for the predictive performance. I saw also, not all of you are working with these kind of large P examples, so I saw also small P example where there's less features than N and where they're still useful. Predict body fat percentage. The reference value is obtained by immersing person in the water. And then there are many cases where you would prefer to use much smaller instrument. And the smaller instrument is device measuring how much fat you get pinched, for example, from here. So this Siri, it's computed based on this what is your weight in water. So it can take into account your volume. And the rest of all the available coverage, age, weight, height. And then the rest of these are these pinch measurements. And so that if you have more fat, you get more thing pins there. And you can see that these different measurements are highly correlating with each other. And so which one of these we should use if we want to make quick body fat estimates? For example, if some person comes to and here are the marginal posterior coefficients. So abdomen, yes, let's use that. Maybe nothing else. And why this is so wide? Bivariate. Height, weight, strong correlation. 0 is away from the typical set. So maybe the weight would be useful after all. These come from projpred packets, these plots. So it makes number of variables in the submodel. There's the reference model, root mean square error, reference model, expected log predictive density, 0 variables, adding abdomen, big improvement, adding weight, and we have the same performance as the full model. We can do projection. So we have abdomen and weight, and now in the projected model, clearly away from 0. Just for visualization, again, these are the projected constraint, that the height and all others are 0. Here's a difference that what if we would just refit a model using only this weight and abdomen pinch. Conditional on submodel, we get smaller sigma. So it's compared to projected. I should have also put here the full model, I now realize, but you can see now that in a way they did it. Conditional on submodel, it's underestimating the variance. We have also a paper on using this for graphs. Here's the projection result for CEU genetic network. You can use also for smaller networks. Nice performance, and then these look a bit messy. Here, graphical lasso tends to have worse estimates for the coefficients found, and here we have good balance there. There's a list of references where you can find more results, and then take-home message for part 2. So sparse priors do not automate variable selection. We can't trust marginal posteriors if we have correlating variables. So we should make first that big model, including all the information, reference model, and then we can use projection. I showed only now how to choose the minimal subset, but if we remove that minimal subset and then repeat the projection, we can find also all the relevant features. Currently, we have the projpred package. You can use not just with Stan, also with other packages. We have there that now it works best for generalized linear models. It can be used also with other model families. We have also paper for Gaussian processes. Reference model can be actually anything. It's just that now we have only code for doing that the projected model has to be currently GLM in this projpred package. For the Gaussian processes, we don't have package, but the projected model is also Gaussian process. There's also some theoretical discussion, kind of conditions when using reference model helps in this paper. R package in CRAN and GitHub, easy to use with rstanarm BRMS, and there are a lot of case studies here in the model selection directory, and then you can find also there additional videos, for example, the regularized Horseshoe and many, many case studies. Thank you.